used method of shuffling cards in at least Western society is the riffle shuffle, which you cut a deck of cards about in half. So how do you make mathematics out of it? Here's how you do it. You have a deck of cards that's ordered to end to start. You cut off about half, and mathematically you cut off C cards with probability n2c over 2 to the n, the discrete version of the bell-shaped curve. So you cut them about in half, and then you start dropping them with your two thumbs, the way you do when you shuffle cards, according to the following rule. If at any stage you have A cards in your left hand and B cards in your right hand, the chance of dropping the next card from the left is A over A plus B. So you drop cards with probability proportional to packet size, and then they shuffle. Does that make sense to everybody? I hope. So that describes a probability, a way of mixing it if you run out of cards and the rest drop. And so I try to say that here. A and B, drop the next from the left with probability A over A plus B. It's quite a good model for the way real people shuffle cards. It's not a good model for the way I shuffle cards. It's almost perfectly. It's not good if you shuffle a deck of cards perfectly 8 times, it comes back to where it started. So that's not a good way of mixing. This is probably the fastest way of shuffling in the sense of maximum entropy distribution on shuffles. That's shuffle once. Okay, of course we repeatedly shuffle, so we'll make this verbal description into a formula soon. But let Q of sigma be the chance of sigma after one shuffle. Sigma is a permutation. Q of sigma is the chance that after one shuffle there's a permutation sigma. So that's a probability distribution. Permutation group. Shuffle twice. That's the notation for it. What's the chance that the deck is in arrangement after 2 shuffles? Well, it's just given by convolution. You have to have done something your first shuffle, eta, and then you have to chosen the shuffle that takes you to sigma from eta. So that's shuffle twice. And you can imagine that you can involve shuffle k times. I'll use this Q convolved with itself k times. And there's also, the cards are all mixed up. That's the uniform distribution. And that's U of sigma is 1 over n factorial. And an early theorem in the subject, that good upon already actually, is that Q star k of sigma goes to the uniform distribution. That is, if you shuffle a deck of cards a lot, it gets all mixed up. Now you already knew that, right? But it's a question how fast the symmetric group, n factorial is 10 to the 68 or something like that. And so how many times do you have to shuffle? And here my proof with Dave Fire a long time ago goes like this. So let K be 3/2 log to the base 2 of n plus C. Let's try to parse that for you. N is the deck size, N is 52, and K is the number of shuffles. So you know K and you know N. So that determines C as a function of K, and that's the C that's going to come up. C can be negative or positive. C is C. And then the distance to uniform, the standard variation distance that we use in probability, the theorem says that that is describable, and it's a very good approximation. This is a formula for it, 1 minus twice normal distribution evaluated at length 2 to the minus c over 4 times the square root of 3, and then there's an error term. Let me try to, and where this phi of x is the area under the bell-shaped curve to the left of x. So if C is big, say C is 5 or something like that, 2 to the minus C is small, and the normal curve is symmetric about 0, and so phi of 0 is 1/2, it's multiplied by 2, so that's 1 minus 1. So it's going to zero. So this C is the same as this C, and that's hard formula to parse. But what if you draw a graph in which this is the number of shuffles, and this is how close to mixed you are. The graph looks like this is flat for quite a while, and then it cuts down at 3/2 log to the base to a bend, and then it goes to zero exponentially fast. So that's zero, and the proof of that, we needed a richer notion of shuffling, and it was A shuffles, and so let me describe an A shuffle to you. I told you what a 2 shuffle is. What's a 3 shuffle? A 3 shuffle, you've got a deck of cards, you cut it into 3 piles, binomial distribution, cut it into 3 piles, and then with your 3 hands, start rippling, dropping cards with probability proportional to packet size each time. If you don't like that, you can take the first 2 piles, shuffle them together, and then take the 3rd pile, shuffle the big one. It's the same thing. And so that would be a 3 shuffle, and similarly, understand the idea of an A shuffle. Right? Cut the deck into 8 piles and then shuffle them together. Do that however you like. One of the things we discovered in proving this theorem was that these measures convolve nicely. That is, if you do an A shuffle, you follow it with a B shuffle, that's the same as doing an AB shuffle. It's good. That sounds nice. So I just wrote that down. Q of A times B convolve it. And once you discover it, it's not hard to see that. And so K shuffling K times Q star K is the same as Q 2 to the K. So you only have to know about A shuffles. I don't have to know about convolutions. I only have to understand A shuffles. That's good too. And then a miracle occurred. There's a formula for what's the chance of being in a permutation after an A shuffle. And it's a nice formula. There it is. So Q sub A of sigma, the chance of being at sigma after an A shuffle, is given by a binomial coefficient n plus n minus d minus 1. Choose n. You might say, wait a second, there's a sigma on the left. There must be a sigma on the right. And there is. D is the number of descents in sigma inverse. And that's a nice formula. And discovered it first empirically by looking at data, guessed at it, and then once you, again, have a clear guess, it's not so hard. So that's a little bit of the background that we need in order for me to tell you what Richard did. Okay, so that's a little bit of introduction to riffle shuffles. So what did Richard do? It's pretty easy to explain, at least the statement. I now am going to have, instead of A as a general vector, so let omega be an infinite tuple, omega 1, omega 2, etc. And omega I are non-negative, and they sum to 1. So it's just some countable probability distribution. Drop n balls into infinitely many boxes with probability omega. So many of the boxes are going to be empty, but the chance of a ball dropping into box 37 is omega 37. It's a probability distribution. Makes perfect sense, right? Drop n balls into infinitely many boxes according to that multinomial distribution. So let n1, n2 up to n whatever it is be the box counts in the non-empty boxes, and cut a deck of cards into n1 piles, n2 piles, nk piles, and then shuffle them together. Okay, just by the same Gilbert-Shannon-Reed's measure. That's an omega shuffle. So a special case, of course, if the omega is 1 over A, 1 over A, 1 over A, and with zeros, then that's the old A shuffles. This is just, it's got a little bit more freedom. And what Richard did, and this just knocked me over, is the following theorem. So pick sigma, pick a permutation at random from one of these omega shuffles. So just do that. And now do what is natural for all of us to do, pass sigma into a partition by using the Robinson-Shenster algorithm. Okay, so that is take sigma and you have a pair of standard Young tableau, they have a shape, call that shape lambda. Pick a shuffle and then look at the RSK shape. And his theorem says that the chance of having the shape lambda is equal to this number, f of lambda times s of lambda of omega, where f of lambda is the dimension of the lambda's representation, irreducible representation of the symmetric group, and s of lambda is everybody's friend, the Schur function. So even now, it's a long time ago that he did it. I just couldn't believe it. First of all, where did it come from? I didn't guess at it. So one thing it does is it gives a probabilistic interpretation of the Schur function. The Schur functions, when you meet them for the first time, they're defined by alternates or this nice formula is the sum of standard Young tableaus. It's not something you can tell children about. Shuffling, you know. So that's one thing, but just as a fact of nature, you know, it's not asymptotic, it's all the way. Okay, so what now? So what? It's beautiful, that's enough, right? Well, here's a little bit more. What does Richard's theorem say in my world of shuffling? So I'm going to give you two examples of what is it good for in my part of the world. I don't know if you can see this, but I'll say it. If you have a permutation, there's a famous thing you can look at, a statistic, which is the length of the longest increasing subsequence. Okay, and many of you know that that's the number of boxes in the first row of one of the okay, and L of sigma has all kinds of interpretations. In particular, if you have a hand of cards in bridge, if you can take cards out and then put them back, sort them by insertion deletion operations, the number of insertion deletion operations it takes is n minus L of sigma. And so it's something that has legs not only mathematically but in practice. It's called Bloom's metric. So one can ask, suppose you shuffle cards, what's the distribution of the length of the longest increasing subsequence and how long does it take to get to its limit? I don't know if you can see this, but I'll say it and then. So here's a theorem and it follows with work of Kurt Johansson and Jason Pullman and I, but it wouldn't have been absolutely impossible without Richard's connection, which is, I'll say it with ordinary riffle shuffles. Suppose you two shuffle cards, you shuffle a deck of 10 cards k times, okay, then look at the length of the longest increasing subsequence, L of sigma. If the cards were really well shuffled, that should be about 2 root n, if you divide that by n to the 1/6, that has celebrated limit distribution. And what this says is that n is large. If k is large enough, of course, the deck is close to random. How many times do you have to shuffle to get the same limit loss? So let's say, so the chance of L sigma minus 2 root n over n to the 1/6, the metric scaling, this converges to the Tracy-Whittam distribution. I won't try to explain that, but it's one of the hot items in probability. When k is 5/6 log to the base 2 of n plus c, c comes into the error term. So first of all, that's a real theorem about shuffling. And what it says is that features of shuffling, in particular, the length length of the longest increasing subsequence get random faster than it takes for every thing to get. And then once you see that, you can say, well, okay, how many times do you have to shuffle to make the top card? Where the ace of spades, suppose it starts on top, how many times do you have to shuffle until that gets random? Answers log to the base 2 of n is faster. How many times do you have to shuffle to make the card on top random? That's different. It's a half n. And there's a whole world of those kinds of theorems, and this is one of them. It connects subject that we know and love to observable probability. Here's a second consequence. So this is a separate story. So here's my deck of cards in order, right, 1 up to n. And suppose I shuffle them once. Okay, there's got to be an increasing subsequence of length n over 2. Because this is in the same order, and this is in the same order. And however you cut them, one of them is bigger than or equal to n over 2. So there's got to be an increasing, after one shuffle, there's got to be an increasing subsequence of length, at least n over 2. After 2 shuffles, there's got to be an increasing subsequence of length, at least n over 4, because you cut into 4 piles, shuffle, and each of those piles is still increasing. And now, but at least, maybe the top n over 4 cards, they go in someplace, but some other cards that go underneath them, and the length of the longest increasing subsequence is a little bit bigger. How does it go? That's a question. That is, suppose I only do 2 or 3 shuffles. What's the distribution of the length of the longest increasing subsequence of the? Okay, so here's a theorem, and this theorem again, it follows from this translation from shuffling into symmetric function theory, and then it follows further from Berger, Sergei Kirov, and some work by us too. And I'm going to tell it to you in the cleanest case I can. Suppose omega is 1 over a, 1 over a, 1 over a 8 times. So that's an a shuffle. So it could be 1 over 2 to the k. 1 k 2 shuffles. Pick a permutation from q omega, that is do an a shuffle, and then look at the RSK shape. But now no asymptotics of that sort. So let sigma go to the shape lambda by RSK. Then the length of the longest increasing subsequence is going to be comparable to n over a. And what this says is, so look at the number of boxes in the first row, subtract off n over a, and then standardize it by root 2n over a. What's the chance that that's less than or equal to x1? The number in the 8th box minus n over a is less than or equal to. So look at the lengths of the boxes in RSK, they'll be 8 of them. And what's the joint distribution of those? And the theorem that we proved says that when n is large, but it's good convergence, it's not a bad result. The chance that happens is equal to, or the limit equal to, the chance that some other thing happens, that a to 1 is less than x1 times a to k, a to a is less than xa, where a to 1 up to a to a are the eigenvalues of a random matrix in GOE, I guess, and 0 is traceless matrix. So there's a whole world. It's of random matrix theory and the standard ensembles. And this is one of the standard ensembles. But this is an A by A matrix. So pick an A by A matrix, and look at the eigenvalues of it. Those are any numbers. And we know more or less anything we want to know about these data. And that's what the boxes of RSK look like. So you should be saying, matrices have to do with, of course, the symmetric functions in between. Here's an example. Suppose I shuffle once. Okay. I just do one shuffle. It's a deck of cards. It's in order. Just do one shuffle. So one of the two piles is bigger than number two, and then maybe something else happens. So the theorem says that L of sigma, the minus n over two, with fluctuations root n, what's the chance that that's less than or equal to x? It's this is the limit. It's a Maxwell distribution, a gamma distribution of two. And so you want to know what's the chance it fluctuates between two limits, that tells you. So those are two consequences of Richard's discovery in my world of shuffling. So, okay, now this is a little important. Good. I feel on time. Let's see. That'll Tom. Big deal. Sorry. Okay, so here's a new topic, but I'm not going to do too much about it. The characters of Sn and S infinity. So we all know that for two partitions, lambda and mu of n, there's the character of the lambda irreducible representation at the muth conjugacy class, and that's some number, real number. And those of us who do analysis on groups, that's me, need to know what those numbers are. We work with them, really need to know what they are. And here's an example. Due to Frobenius, the lambda character of a transposition has n minus 2 fixed points and one transposition. It's given by this formula, 1 over n minus 1, the sum of the parts of the partition, squared minus 2j minus 2i. This should be 2i minus 1. Should be I, but it's a little quadratic formula. So that's a formula, right? I mean, you can work with that, but it's a formula. There are similar formulas for 3 cycles, products of 2 cycles, 4 cycles. If you have an n cycle, we know. So sometimes you can get your hands on characters, but before anybody gets too enthusiastic, for general lambda and mu, deciding whether the character is 0 or not is and I'm going to say NP complete. That's not right, but if you want to know what is right, ask your pack or Greta Panova. They have a very, very careful study of this asymptotic complexity that they're interested in for characters. And basically, you can't do it in general. That's the takeaway. So that's what we're interested in. And so here's an aside. Suppose G is any finite group, and it has characters, ordinary characters over C. And suppose I normalize it. That is, I just divide by the value of the character at the identity. So the normalized characters of the group, they satisfy 3 properties that you all know. First of all, they're normalized. That means that the identity 1. And the second thing is they're symmetric. They're class functions. Chi bar of ST is the same as chi bar of TS. And the third thing, maybe a little less familiar, is that the matrix is positive definite. That is, look at chi bar, SI, SJ inverse, and multiply it by any complex numbers of this sort. That's bigger than or equal to 0, so that matrix is positive definite. And this is a convex. This normalized characters form a convex set. So a theorem, which I don't know who to attribute to, I'm calling it folklore, it's an old theorem, is that the extreme points of this convex set, it's a compact convex set, the extreme points are the irreducible characters. Anybody get it? No, I mean, some people. Okay, so that's a way of thinking about characters, and go on. Okay. Yeah. Okay, so now let G be any group, could be quite a big group, like S infinity. Right? Consider the class functions from G to C, which satisfy those three properties. Okay, that is again a compact convex set, and people define the extreme points of this set to be the normalized characters of G. Okay, that's people who work with big groups call that. And a beautiful theorem in the subject, Thomas' theorem, says for S infinity, the extreme points are indexed by numbers omega, and omega is broken into two parts. There's alphas and betas. Alpha 1 bigger than or equal to alpha 2, make the monotone, beta 1 bigger than or equal to beta 2. The alphas and the betas are non-negative, and their sum is less than or equal to 1. And the wonderful thing is that, so for each omega, there is an extreme point, a character of S infinity, and the character, the omega character of sigma has a nice formula. And that's a nice formula. That is, sigma has k cycles. You raise the you raise alpha I to the k power and sum that over I, raise beta I to the k power and take the difference. And so that's a nice formula. It's a formula where the characters of S infinity, and it does approximate, there is an approximation theory saying it usefully approximates the characters of Sn, because after all, S infinity is the limit of Sn. And then you can ask, well, how does it go? You know, for example, if alpha 1 is 1 and everything else is 0, that's the trivial character, right? That's identically to 1. If alpha 1 has got a 1, beta 1 is 1 and everything else is 0, that's the alternating character. So you can ask, can we understand those characters? Ripple shuffles and Richard to the rescue. Okay. Take the omega character, maybe omega is half a, but omega is of course anything. Take the omega character. If you restrict it to Sn, well, it's a character of Sn now. So it's a linear combination of the characters of the normalized characters of Sn. So there are multiplicities or weights, weight partition lambda of omega. So these weights are non-negative and sum to 1. And the theorem of Jason-Fullman, which I find wonderful and interesting and remarkable, is pick sigma at random from that measure, Richard's measure, q sub omega, and change sigma to lambda by RSK. The chance that that measure assigns to lambda is exactly this way. It's not an asymptotic, it's equal. Well, we know a lot about shuffling. Character people know a lot about the weights. There's a close connection, shuffling and very nice match. I'm going to end now. I should have ended minutes ago, but I'm not going to do that. Here's a summary. So Richard's insights into ripple shuffling contributed at least 3 things. There are new results about shuffling. There are new results about symmetric functions, probabilistic interpretation of symmetric functions. And finally, there are new results about the characters of S infinity. So suppose you wanted to read more about this or see some details, that sort of thing. Here are 4 places to look. Everything I just told you is in the book I wrote with Jason. It came out, Mathematics of Shuffling Cards. Jason's theorem about the connections between shuffling and symmetric functions are in a very, very nice paper, Applications of Symmetric Functions to Cycles and Increasing Subsequences. If you want to know about S infinity, there's no better place than the beautiful book by Alexei Borodin or Olshansky, representations of infinite symmetric group. I taught a course out of it. It's worth looking at it if you don't know. And finally, Richard's paper appeared 20-something years ago, generalized ripple shuffles in quasi-symmetric functions. I think all of us are indebted to Richard. This is one of the many ways that I